Well, I guess we might as well get started. There's only one person in this tutorial, so lucky you, Felix. You get to be you get the private tutoring for today. All right. So today's lesson is going to be about range trees. I'm going to assume we all know. I say we, but it's only one person. It's so weird. Okay, I'm assuming you all know how to code a range tree, since this has been taught. This has been taught for a couple of weeks now. Also, today we only have one problem, so today's lesson is going to be a little bit more relaxed. Something I'd also like to point out is that the tutorial code is actually online now. So if you go to Moodle, and go to tutorial problems, you can see that now we have a bunch of different tutorials for every single, a bunch of different time slots for every single tutorial. So we are W15A, so if you want to check out, let's say, EHAB's last corollary, the code from last time, you can click the link and you can check out what we did last time. Yeah, so this will generally update within like a day or so of the tutorial finishing. So since that's kind of a long time, I'll still post the pastebin links during my tutorials so that you can get the code faster. Finally, what I wanted to say was that recently, since I updated my MacBook, I have received a crash where I needed to restart before. And so apparently it looks like this is a repeating sort of error that people get. So if I disconnect during this lesson, just trust that I'll have my laptop restarted in a couple of minutes. So you can just sit tight and I'll be right back. Anyway, let's go on to today's problem, which is water tree. Okay, so I'll explain the problem. Mad scientist Mike has constructed a rooted tree which consists of n vertices. Each vertex is a reservoir which can be either empty or filled with water. The vertices of the tree are numbered 1 to n, with the root at vertex 1. For each vertex, the reservoirs of its children are located below the reservoir of this vertex. The vertex is connected with each of the children by a pipe through which water can flow downwards. Okay, so what does that look like? This is basically just a tree. So we'll draw a tree like this. It's going to be rooted at node 1. We're given that. Root at vertex 1. So let's label the tree like this. For every single node, we have a pipe that goes down to its children. Like this, so water can flow from the top reservoir down to the bottom ones. Okay. Mike wants to do the following operations. We have a newcomer. Hello, Alfav. It's getting a bit lonely here, so I'm very glad that you came. Here is the problem link for today. All good, all good. So you didn't miss much. I'll just restart explanation. Basically, we're given a tree. It is a rooted tree rooted at node 1. That's really all you got up to so far. So you haven't missed much at all. Okay. So Mike wants to do the following operations with the tree. It has 3 different operations. Fill the vertex V with water, and V and all of its children are filled with water. Number 2 is we empty the vertex V, then V and all of its ancestors are emptied. Number 3 is we determine whether vertex V is filled with water at the moment. What does this look like? Filling a vertex will fill its children as well. So let's say we fill vertex 1, and vertex 2 and vertex 5 are also filled. Then since these are filled, then vertex 3 and vertex 4 are also filled, and so on. So in other words, step 1, when we fill a vertex, we basically fill every single other node in its subtree. Step 2, we empty a vertex V. V and all of its ancestors are emptied. So for example, if we empty 3 right now, then 3 is emptied, 2 is emptied, and 1 is emptied, right? The ancestors are left with something like this. Finally, we determine whether vertex V is filled with water at the moment or not. Okay, so initially all vertices of the tree are empty. Mike has compiled a full list of operations that he wants to perform in order. Before experimenting with the tree, Mike decided to run the list through a simulation to help Mike determine what results will he get after performing all the operations. So we have an input. The first line of the input contains an integer n, which is less than or equal to 500,000, which is the number of vertices in the tree. Afterwards, get n-1 lines containing two space-separated numbers a and b, which represent the edges of the tree. Next line contains a number q less than or equal to 500,000, number of operations to perform. Each of the following q lines contains two space-separated numbers, ci and vi. Ci is the operation type, so it's either 1, 2, or 3. And vi is the vertex on which the operation is performed. It's guaranteed that the given graph is a tree. Our output for each type 3 operation, we print 1 on a separate line if the vertex is full, and 0 if the vertex is empty. Print the answers to the queries in the order in which the queries are given in input. So as an example, this is a sample input here. We have 5 nodes, then 1 is connected to 2, 5 is connected to 1, 2 is connected to 3, and 4 is connected to 2. And you'll find that this is actually just equal to this graph we have here. Then we have 12 queries. So we won't go through all of them, but we'll go through like the first 3 or so. The first query is of type 1, and we affects vertex 1. So it's a fill command. We fill vertex 1. So we start at the top, fill these vertices like this. As we fill 1, everything else gets filled. Next query is we have to empty vertex 3. So this is just like we did before. Empty vertex 3, and we'll remove the ancestors. And we'll empty its ancestors as well. Finally, step 3, you have to check whether node 1 is empty or not. So node 1 is empty, so we print out a 0. Here we check, afterwards we check 2, 3, and 4 to see if they're empty. 2 is empty, 3 is empty, and 4 is not empty. So we should print 0, 0, 1. Right. So hopefully that explains the problem. I'll give you another 5 minutes to think about this problem in general, as well as answer any questions you have about this problem. So you'll have until 3:19. Okay, so hopefully you had some time to think about this problem now. So let's start with some naive solutions. So what might a naive solution look like? Yeah, exactly right. So Felix, update children every query in linear time. That will handle operations of type 1. Right? We can do this just by doing a DFS. So when we fill in a node, just DFS downward the tree and fill in everything in its subtree. How do we handle operations of type 2 then? Yeah, exactly the same way. So instead of the children this time, though, you'd have to do the ancestors. And what we'd have to do is we'd have to store a separate tree, which has all the edges in reverse. And so when you empty a node, let's say this one, we just traverse up the tree, DFS up it, and then we can set every single other node above that to 0 as well. Finally, checking is a constant time because we're basically going to be keeping track of whether each node is filled or not and manually filling and unfilling them every single time. Since this is order n, number 2 is order n, number 3 is order 1. In the worst case is an operation takes order n. So if there's q operations, then we get the complexity of qn. So this is 500,000 squared, right? N is 500,000, q is 500,000. So the complexity is too big. So I don't even need to calculate it just to know that 500,000 squared is going to be too slow. Okay, that's the naive solution out of the way. Before I continue the lecture though, I wanted to ask, who has actually watched the lecture on Monday? I know it's just been 2 days since, but raise your hands if you've watched the lecture. I expected as much. Yeah, it was kind of the same for my last class as well. About half the students didn't actually watch the lecture. That's totally fine. That just means that I have to explain a little bit more during the tutorial as well. Okay, so I need to explain a couple of things for this problem. It's a couple of new techniques that we're going to be learning about range trees. I'm not going to be giving like the best like explanation ever. I'm not going to give like all the proofs or anything like that. I'm going to leave that for the lecturer yourself. So I'd highly recommend that you actually do go to the lecture afterwards and check that out. But if I can just get a rough idea or a general idea, just the things enough so that we can actually code it today, I think that would be sufficient. Okay, so the first thing we want to do is to learn about a range tree over a tree. So I did mention that today was a range tree day. You might be looking at this tree and you might be wondering, how can I possibly put a range tree over this, right? Normally for a range tree, you have an array and you'll do some sort of point update. So you'll update a very specific node, then you'll query a range of it. So for example, find the sum over a range, right? But this is only for a 1D array. So how can we possibly use a range tree when the problem is given as a tree, right? This sounds like graph theory, not range trees. So this is what we're going to be actually tackling today. So first technique we're going to be learning is range tree over a tree. Okay, so the range tree over a tree solves the following problem. In a tree with n nodes with initial value 0 and 2 queries. We have to handle 2 types of queries. First one is an update. Given a node, add v to it. Our second one is a query. So find the sum of the subtree. I'll actually change this. I'll change this to a set to V instead. Yep. Okay, cool. So imagine you're given the following problem and you have to do both the updates and the queries in log n time. So once again, we know this is a range tree, but how can we actually use a range tree to query subtrees, right? That doesn't quite make sense. Well, as it turns out, there's actually a really clever way that we can convert any tree into a format where we can do range trees over the subtrees. The way we do that is to find a DFS pre-ordering. So this is what we're going to do. We're going to do a DFS from the root. And every time we first see a node, we're just going to write it down. So for example, we'll have, we'll start at the top, which is 1. Then we'll move to 2. All right, we'll check. Start at the top, which 1 is the first time we've seen it, so we'll put it into our pre-ordering. We'll go to 2, then 3, then back up to 2, and then 4. And back up to 2, back up to 1, and then to 5. Right, so this is the DFS pre-ordering, which I'm sure you're all familiar with. And so we get the pre-ordering 1, 2, 3, 4, 5, which is actually very nice, very convenient for us. Okay, so once we have this pre-ordering, one thing you might notice is that all subtrees are represented by consecutive ranges in our pre-ordering. Notice, for example, that the subtree of 1 is given by this consecutive range. Subtree of 2 is given by this consecutive range. Subtree of 3 is given by this consecutive range. Subtree of 4 is this, and the subtree of 5 is this. This pre-ordering has this very, very nice property that actually allows us to sort of compress subtrees into a 1D sort of line. And now, this is where we can use a normal range tree with the pre-ordering to query points. For example, let's say I wanted to query the sum of the subtree of 2. That's fine. All I need to do is I need to find where the left side of the subtree of 2 begins and where the right side of the subtree of 2 ends. Then I can just query this range. And then that will give me the sum of all the nodes in that subtree. Right? I'll talk about how to actually work out where the left and right side of it is when we get to the implementation part. This is how the sort of DFS over a pre-ordering works. So once we have this pre-ordering, basically this is just normal range tree stuff now. So you should all be familiar with this. Range tree might look like this. And so, of course, when you do updates, you'll just go down to a particular point and set it to whatever value it is. And then when you sum it, you go to the particular ranges. So for example, if I want to sum this range, then I come this node and sum up the 2. These are both recursive algorithms that are just old range tree stuff. You should all know. Okay, so can everyone see how we might be able to answer this question using this technique of range tree over the pre-order? Can I get a yes or no? Great. Okay. Technique number 1. Let's look at technique 2 now. Our second technique allows us to do range updates, and it's called lazy propagation range tree. Okay, so up until now, the range trees that you've normally done update a single point. So for example, I'm gonna move this tree somewhere else. So far, let's say we have like an array like this, and we have to update a node to a new node, or we might have to query a range to find a sum, for example. So far, the range tree that we've done so far have been point updates, which mean we only update a single point and range queries, so we can query an entire range. Now we want to solve a different problem, which is what if we want to actually update an entire range at a time as well? So for example, maybe we want to set all of these to 1, and then we want to query the sum of this range over here, right? So if we just used our old range for this, well, then potentially we'd have to update up to n nodes per range. So that would take n log n. But we want to do it in log n. So we want to update an entire range in log n time. So let me once again set up a sort of problem that we can sort of work through together. And our sample problem will be given an array length n with initial value 0 and q queries. We have to handle the following 2 queries. So first one is an update given a range, set them all to b. And our query is find the sum of a range. Actually, I'm going to change this a bit. I'm going to I'm going to do add. Add v to all elements in that range. Okay, yeah, I'll do it like this. Okay, so what might this look like? So maybe I will start at all zeros. And I say, okay, I want to add 3 to everything in here, right? So we'll set these all to 3. Then I say, okay, I want to add 2 to this range here. This becomes 2 and this becomes 5, right? And finally, for my query, I'll see like, okay, I want the sum of this, and this return 11. That's the sort of sample problem that we've got to set up, and now we have to actually do it. The first thing we should do is we should construct our range tree over it. Our range tree is going to look like this. Okay. And we'll reset everything to 0 as well. Since this is a range tree and we need to do the sum of the range, then we can just make sure every single node stores the sum of its range it covers. So for example, this node covers this range, so it'll just store the sum of that range, right? So clearly when we do queries, this is going to work because all of the values are correct. Okay, so now how do we actually do these range updates? This is where this lazy propagation idea comes in. So first off, for a range tree, we need to tell every single node what the value is, right? So we'll have an array called RT. We'll label these nodes 1, 2, 3, 4, 5, and so on in level order, right? So label them like this. I'll make them a little bit smaller, so a little bit more out of the way. And so node 0 will correspond to here. Node 1 will correspond to here. Node 2 will be here, and so on, right? Now we'll actually store some extra additional information for every single node. The first one will be called dirty. The second one will be called dirty add. If you actually go to the lectures, I think the word they use is lazy, not dirty. But I like to think of them in terms of dirty nodes and cleaning the dirty nodes. If you ever go to the lectures, then you can pretty much just replace dirty with lazy. And then that's sort of how you translate from this tutorial to the lectures. So the dirty and the dirty add are both going to be arrays as well. Dirty is going to be a Boolean array, and it will mark whether the node is dirty or not. Dirty add is going to be an integer array, and it's going to mark how much we need to add to this node, as well as all the nodes in its subtree. To begin with, everything is just 0. None of the nodes are dirty, so everything is clean. The dirty add is all as well. Okay, how does an update work? So let's say we want to update this range over here. Move this down a little bit. Maybe shrink it. Whatever. Okay. So let's say I wanted to update this range and I wanted to add 3 to every single thing in this range. Here's what I'm going to do. So I'm going to do a normal, sort of like a range update. So I'm going to find the nodes that cover this range, right? I know that getting to here is log n time from our previous range trees. We're going to find these 2 nodes, and what we're going to do is we're going to make these nodes set to the correct value. But since I'm adding 3 to this node, we know that this node gets the correct value should be 3, right? Also, since I'm adding 3 to everything under this node, what should the correct value be? 6, right? Because we know that this node actually covers 2 nodes. So it's actually really easy to calculate how much what the correct value should be if we were to set everything here to 3. That's because as we go down, we can keep track of, rather we can just look at the size of this node and how many nodes it covers, and multiply that by the amount we're going to add to get the actual correct value. So we have this invariant that 30 nodes are correct. And actually just done. When we go back up the tree, we'll do what we normally do, which is we'll update the nodes as we go back up in the recursion. So this gets set back to 3, and this gets set to a 9, right? So notice how, this is actually just the full update. Notice how these nodes hold the correct value for the tree, but these nodes aren't actually updated yet. Right? These guys should be free, but they're not right now, right? All we've done is we've marked this node as dirty. We've marked this node as dirty. We'll also need to make a dirty add value of 3 as well here as well. So if we come here, we're going to mark it as dirty and update the dirty add value. But once we do that, we're done. So we just quit. We don't bother to actually make the whole tree correct. This is where the lazy part of the lazy propagation comes in, right? We're being lazy, we're making nodes dirty, but we're not going to clean them up right now, right? So we're just going to leave a dirty tree there. So one thing we can notice is that a node only holds the correct value if none of its ancestors are dirty. For example, this node here, you can see that none of its ancestors are dirty, so it's holding the correct value. However, for this node over here, one of its ancestors is dirty, so now it's holding the incorrect value, right? You can't trust the value here because there's dirt above it that needs to get pushed down first. Okay, so that's how we do a dirty or a range update. And now we have to look at a query, right? So here the query is find the sum of a range. So let's say we want to find the sum of this range right here. Just a single range, right? A range of length 1. And normally, if we were just to ignore the dirty values entirely, we come down to here, we find this node, and then we'd add this onto our sum, right? Which is 0. But the problem is that technically all of these elements are free, right? And as before, this node doesn't actually hold the correct value, so we can't trust it. How do we actually fix this issue? Well, the way we do it is by propagation, and this is where the propagation part of the lazy propagation comes in. So our query is going to start at the top. Basically, what we're going to do is that we're going to what's called clean or propagate for every single dirty node that we see. If we start at here, right? Well, this is clean, so we don't have to do anything. We come to here and we see that this node is dirty. So every time we see a dirty node, we have to clean it. What does cleaning mean? Well, it just means that we propagate the dirt down to its children. So we know that this value is correct, so we don't have to touch it. So we'll just set the children to dirty instead. We'll say, okay, you two are dirty, and you have a dirty add of 3. So we've now marked this node as not dirty anymore. It's clean now. We push the dirt down into its children, right? So when we push the dirt down into its children, we also have to make sure that their values are correct now. So since we're adding, since we're setting everything in here to 3, or rather we're adding everything in here to 3, we'll just add 3 to whatever was in those children, right? Also know that those children cover exactly 1 node each, so we just multiply that by 1. right? 3 times 1, and we add that onto the zeros. We get 3 and 3, right? And we go down again. This node is dirty, so we have to clean it. Since it's a leaf, we can't actually propagate it down to its children, right? So we just clean it, and we know that this value was correct since we did it earlier. So we can just use this value now. So the range of this, the sum of this range is 3. So notice how every time we go down, we actually clean the node. This guarantees that when we actually get to a node, all its ancestors are clean, right? And so what that means is that, remember what we said earlier, if all the ancestors of a node is clean, then the node holds the correct value. So this sort of cleaning as well as the sort of dirty thing together in tandem basically means that whenever we query, we'll actually get the correct value for our range tree. Okay, so let's do another example of an update just so we can see what's going on. Let's say we update this and we want to add another 2 to it, right? The end result would be 3 and 5. So what we'll do, we'll start at the top again. Okay, well, the range is to the left of here. So I'm going to go down here. And this node matches the range. So we found the correct node. So we'll mark it as dirty. We'll make the dirty add 2. And then how much do we have to add to this node? How much do I have to add to 3 to make this node value correct? It's 4. The reason why it's not 2 is because, remember, this covers 2 nodes. So this actually becomes 4. So this becomes 7. I messed up here. This should be a 2 since we're adding 2 to everything. Right, and so you can see the 7 is actually the sum of the 2 and 5, which is, of course, correct. Okay, this should be 3. And so now we're done, right? So we found a node. And now when we go back up, we just have to remember to update everything. So 7 plus 6 is 13. Yeah, just make sure every single node is the sum of its 2 children. Okay, so that's the update. One more time. Let's do something special. Let's try to query this 5 here. Once again, we'll start at this node. We'll go down to 2. And we'll see, okay, this is dirty. I need to clean it. So we move the dirty value down. Move it here to 2. And we'll make sure we update the value here too. And now we have actually something interesting because when I'm pushing dirt onto a node that's already dirty. So first off, we should update the value. So since we're adding 2, we have to make sure we add 2 here as well. Then what should we do to the dirty value? Do we just override it to become 2? Should we do something else? Right, exactly. So Felix says add the 2 dirty values together, which is exactly correct. The reason why we add them together and we don't just set it because if you can imagine there's more nodes under here, so this is just like a possibility, right? If there are more nodes under here, we're not adding 2 to all of these nodes because these guys haven't been updated yet. We need to add 5 to them, right? Because we had an update of 2 and then we had an update of 3 as well. You gotta make sure the guys below actually get 5, not just 2. Okay, finally, so when we're doing addition, you have to make sure that we add the dirty values together. There's actually a common trap when coding, so be careful about how you push dirty values onto the dirty values. Anyway, the query will come down to here. We'll clean this up. There's more places to propagate it to, so this node just becomes clean. And we'll find this value 5 and then return up to the top with the value 5. Okay, so that's going to conclude the lecture part about lazy propagate. Are there any questions about this now? We all understand at least the gist of how a lazy update range tree works. Okay, yes or no? Okay, that's good. Hopefully, if you're still figuring out, we can get the coding will maybe clear it up a little bit better. Okay, so that's how we're going to be doing a tree over a tree and lazy propagation range tree. Okay, great. Let's get back to solving the problem now. We'll come back here. And so obviously, the first thing we want to do is we want to get the DFS pre-ordering. So 1, 2, 3, 4, 5. So now let me pose to you a sort of simplification of the problem. Because of course, we like to consider simpler versions of the problem first. So let's try to solve this problem. We only have to deal with type 1 and type 3 operations. In other words, the tree starts empty, and you only ever have to fill a subtree, or you have to check if a vertex is filled with water or not. Can anyone suggest how we might do that after we pre-order a tree like this? Right, exactly right. So we can use the range tree that we're looking at, the range tree that we looked at before, which is the range update, to store a quote-unquote flip value. Basically, what that's going to store is whether the tree is filled at that point or not. So you can imagine a sort of, this is a range tree, but I'm going to draw it like an array. So basically what we're going to do, everything starts at 0, right? Everything's going to start at 0. And now, if I ever want to fill in a vertex, I just need to fill in that subtree with 1s, right? So let's say we fill in vertex 4. Let's do something more interesting. Let's fill in vertex 2 with water. That means that we'll just have a range tree that sets everything in here to 1. So I realize, of course, that range tree that I taught uses add v. This one, we're going to use a set v instead, which is just a little bit different. Right? As we know from range trees, you can always modify them in like small ways to do whatever you want. So sometimes like you can do a min tree or a sum tree or a max tree. A lot of different ways that you can modify a tree to do what you want. In this case, we're going to do use a set. We're going to make the range update a set operation. Right? Kind of imagine how this works in our dirty range tree here as well. We mark a node as dirty. We're also going to store a dirty set. And that just means that when we propagate it down, we have to make sure we set every single node below it to a to that same value as well. Let's come back here. And so, yeah, so we can do this again. So maybe we want to set 1. We can just set this all to 1. And then we can just have our range tree do this. Then all our range tree needs to do is we need to query a single point. So for example, node 5, okay, we'll just query whether this is 1 or not. And that'll tell us whether the node is filled or not. So I'll write out what this solution here. So we need a range update, which will set all the nodes in the range to 1. Now point query will be check if a number is 1 or not. And of course, we'll have to use the lazy propagation to be able to do this range update. Okay, let's move on to the second problem, which will be a little bit harder. What if we only had to, let's say the tree started out all filled, right? So it's all filled with water. And then I gave you only operations of type 2 and type 3. Once again, I'd like to ask, how do we do this problem? I'll give you a little bit of thinking time here. Backtracking to set to 0, but before that, we clean the tree as we go downwards. Okay, so I think you're confusing two things here. So there is the range tree. We have a range tree here, but we also have the original tree graph here. So it's important to not confuse the two. Basically, when you say backtracking to set to 0, I think you mean, okay, well, we set this node to, if we want to set this node to 0, right? Let's say we're all filled. And if we set this node to 0, right? If we set this node to 0, it'll look like this. And we're going to backtrack up the tree. So we're basically going to do that reverse DFS thing that we mentioned earlier. I'm just going to update all the nodes in this tree to 0. But this has actually nothing to do with the dirty and clean tree that we were talking about. That's all part of the range tree that's stored here. Imagine that there is another range tree over here. And this is what's going to hold our dirty values over here. This tree is different from this tree. So just be careful when you're talking about that. Anyway, I think there was a sort of idea there, which was we'll just start at this node and then we'll just go back up the tree and then we'll set all these nodes to 0 with like a point update, right? So in our range tree, we'll set this to 0. We'll look up to, okay, we'll set this to 0. And then we'll look up again, we'll set this to 0. And so that'll sort of update our tree. And then once again, we'll update our range tree. And once again, if we wanted to query, we can just look at we can do a point query at a particular node, let's say node 2. Then we can see whether this is 0 or not. The problem with this is the time complexity. So once again, the number of nodes that you might need to update is n, right? And in this range tree here, so you might have to update n values. Each one takes log n to update. This is n log n per operation, right? Every time we have to enter a node, we potentially have to do n log n. The overall complexity is q n log n, which is too slow. Okay, it's a starting point though. So not quite right, but it's a starting point. Let me actually give you a sort of hint to try to solve this problem. It's going to be actually a very, very, very cool solution to this problem. So let's say all the nodes are filled. Let's say our operation is to empty node 3. Then I'm just going to set node 3 to 0. And that's all I'm going to do. Can anyone tell me how I can check whether a node is empty or filled just by using this information here? Okay, I'll repeat the question. So basically, the way I'm going to handle a empty, right? So we're only handling operators type 2 and 3. So I'm going to handle an emptying of the node by just setting its value in the range tree to 0, right? Everything else is 1. I'm just going to set that value to 0. Okay, so how can I handle operations of type 3 now? So using this range tree here, how can I check if, for example, 1 is filled or not? Think back into the range tree over a tree, where you can actually query over a subtree. Think about how you can use that to solve this problem here. Right, exactly. You can use a range query to check if any of its children, or more accurately, its descendants, are empty. Right. So, for example, for node 1, right, we know that its range, the range that governs its subtree is going to be the full range, right? So if any of these nodes are set to 0, we know that node 1 also has to be set to 0 as well, right? Because one of its descendants was 0. So since one of its descendants was emptied, then all of its ancestors was emptied. So therefore, our current node is also emptied as well. Right, so we can do the same for maybe 2. So if you look at 2, 2, 3, 4, so the subtree looks like this. And once again, see that that there's a 0 in this range. So we know that 2 must be empty. But if we look at 5, for example, we see that there's no 0 in this range. So we know that 5 is not empty. So we can actually use a range query to solve this problem. So let me just write that up. To handle operations of type 2 and 3 only, we'll do a point update, which is set a element to 0, then a range query, check to see if there are any zeros in a range. So doesn't that cause you to look at n nodes in the worst case? No, it doesn't. So firstly, which one are you talking about? So are you talking about the point update or the range query? Range query, right. Okay. So as it turns out, we don't have to. It's going to be log n, not n. Why is that? Okay, well, basically what we're not going to do, we're not going to check, what we're not going to do is we're not going to check individually every single node one by one, right? So in the range that would look like this, and then this, and then this. We're not going to check them one by one until we find a 0. That would be inefficient. We're going to use the power of the range tree, right? We're going to take advantage of the fact that we can do range queries. In fact, what we're going to do is I'm going to actually change this range. I'm going to basically store the minimum of everything in its range in this range tree here. For example, everything starts off as 1, right? Look at the beginning. Everything starts off as 1 like this. And then when I set 3 to 0, right? Oh. Basically going down here, I'm setting this node to 0. And then this node becomes the minimum of the 2, so it also becomes 0. And this node becomes the minimum of the 2, so it also becomes 0. This node becomes the minimum of 2, so it also becomes 0. This is really just a normal range tree, right? It's the sort of range tree that you've seen before. It's just a min range tree. In fact, let me write that down. Right, and so since it's just a normal range tree, we can do the exact same range operations that we're all used to. So for example, if I want to check this range over here, I'll come down to this node, and then I'll find the minimum of the two, and I'll go back up. And we know from the original range tree that this will cover only log n nodes. We'll only ever explore log n nodes. So yeah, that will give us whether a node is empty or not. So we can use that to check whether node 2 is empty or not, for example, by looking at its subtree. So just something to clarify, in case I didn't make this clear already, is that this array that we're having here doesn't actually exist. So we're not actually storing an array, we're only storing this range tree. I'm giving this array here so we can easily see what's going on, but in reality, we can't actually have this array stored because we can't do range updates on an array efficiently. So we'll only be updating the tree here. This is just here for visual purposes, so I can show you what's actually happening. Okay, that's how we handled operations of type 2 and 3 only. Is everyone happy with this solution for handling operations of type 2 and 3? Yes or no? Great. Okay, so let's move on to the full solution then. So we've kind of worked out how to do operations 1 and 2 separately. Now we sort of need to combine them together. So let's just sort of naively do this, and then we can kind of see if there's any problems with that or not. So to handle all operations, we look at the updates. This is a range update where we set it all to 1. This is a point update where we set it all to 0. We can kind of combine them two together by saying range update set all elements to V, right? That's how if you can do a range update, then you can also do a point update just by setting the range to a single point. This range update can set stuff to 1 or 0, so it should be able to handle both of these. And then our thing, we do a point query, check if the element is 1 or not. Range query, check to see if there are any zeros in a range. We kind of combine this both of these together to be a range query, find the minimum of a range, right? And this can answer both of these queries, right? To check if the element is 1 or not, we can just check that range by itself. And if the minimum of one number is just itself, right? We can just check if it's 0 or 1. And for the range query, check to see if there are zeros in the range. Well, if the minimum is 0, then there's a 0 in the range. If it's not, then there are no zeros in the range. That's how we'll handle those two together in one range tree with both range updates and range queries. This seems well and good, but there actually is still a problem with this. So let's say, for example, that we're going to start with all zeros. I'm going to clear out my range tree as well. Start off with all zeros. Let's say I fill in this range here. Okay, so we'll use our range update, set all elements to V, so we'll set these all to 1. That's fine. Okay, and then let's say I set this node, I empty node 3, right? So basically, let me also color this in on the tree as well. So I filled in this range, and I emptied node 3, so these ones are empty now. Actually, I messed up the example. Restart. Okay, let's say we start by filling everything in. Apologies. Let's start by filling everything in. So everything is now filled in. This. Then we empty node 3. And this will empty node 3, 2, and 1. And now, let's say we just fill in nodes 2 and 4 again. So we fill node 2. This becomes a 1 now, right? So what's the problem with this? Which node, if we were to query it, will now give the incorrect value? Let's look at an example here. So after we filled into the 4, I should have filled these in. So after we fill into the 4, our tree should look like this, right? Is there any inconsistencies between which trees are actually filled in and which trees will say are filled in based on our range tree? Node 1 is different, right? So we know that node 1 is empty, right? We emptied number 3 and then we filled in 2. So node 1 should be empty. But when we look at our range tree here, well, if we look at the subtree of 1, there are no zeros here, right? In effect, what our range tree thinks is that node 1 is completely filled. That's not the case. So what went wrong? The reason this went wrong is because when this was at 0, right? We hadn't filled in 2 yet. As soon as we filled in the 2 range, right? Then we overwrote the 0. And so we basically just lost the information that we had an empty node at 3. So I'd like to ask you this question. How do we solve this problem? Before we try to fill in this range with all ones, is there any way that we can handle this 0 so that this mistake doesn't occur anymore? Exactly right. So Felix has got it. We push the min onto the parent of the range. So basically, in other words, if we see a 0 here, then what we need to do is we need to push it up until it becomes the parent of whatever subtree that we're looking at, right? So since we're filling in 2, all we have to do is we have to move this 0 to the parent of 2, in other words, 1. So we'll move it here. We'll set this to a 0, and then we're safe to fill in this 1. And now we have a sort of, we have a correct range tree. We've pushed this 0 up to the top. So I do want you to be careful with your wording though, Felix. So you say push the min onto the parent of the range. That's not quite accurate, right? For example, if we looked over here right now, let's say everything is colored except for 1, which is 0, right? So this would be what the range tree looks like. If we look at the min of this is 1. We don't want to push 1 onto here, right? We fill in this range. We want to keep this as 0. So how do we deal with that? How do we make sure that we only push a 0 to the top if there's a 0 in here? Think back to the range query that we're allowed to do here. So how can we use it? Okay, fine. So the problem with, I guess you could work, right? So yeah, so that's definitely one solution. So what we can do is, what's my example here? Yeah. So what we can do is we can find the min of this range, and then find the min of this, and then if the min is smaller, then we can update this as well, right? That's certainly a correct way to do it. Another way that we could do it as well is first off check to see if there is a 0 in here or not. And we can do that with this range query, find the minimum of a range. If there's a 0 in here or not, then we push it onto the parent. If there's not, then we don't. Right, does that make sense as well as a sort of alternative solution? Okay, great, fantastic. So let's sort of summarize what we should do for every single operation. And then we'll get into coding. So we have this range tree. These values are all correct. And we have to handle 3 types of queries, right? Fill query, the empty query, and the check query. To fill in, check a range to see if there are any zeros. If there are any zeros, push it to the parent of V, and then finally fill the subtree with ones. Okay, to do an empty, what we need to do is update vertex V to be 0. Finally, to check a node, or check a subtree rather, query subtree to see if the minimum is 0. If it is, then the node is empty. And so that's how we'll handle each of our 3 operations. So, hopefully this makes sense. Any more questions about this solution before I code it up? Okay, we'll get into the coding part then. Excellent stuff. So let me just get my code sort of environment set up. Okay. Okay, cool. Let's get into coding. So coding lazy update range trees has always been known to be a little bit finicky, and there's a lot of I feel like little easy mistakes that are very common in sort of in terms of putting up these lazy update range trees. So I'll make sure to point them out as I go along. Okay, first things first, we need to declare some header files. So we get our standard input and output stuff. We will grab, we'll need a vector because we need to store the graph, right? We need to store the graph and then like process it as a tree. You'll need algorithm, since we'll probably need to combine a min of 2 things since we're doing a min tree. We will need C limits because I'll probably need int max to do the min of 2 things. And do I need anything else? Let me think. I feel like there's one more thing that I'm forgetting here. Can't quite put my finger on it, so I will ignore it for now then, I guess. If I forget, we can come back later and see what I forgot. Okay. Main, we're going to look at our input. We're going to get in an integer n followed by n minus 1 edges. Okay, so let's declare our n and q globally. The reason I'm going to declare it globally because I'm going to need n globally as well for a lot of the range tree queries and updates. So I'll keep that there. C and n. For I from 0 to n minus 1, we're going to scan in A and B. I'm going to need to declare a graph for this. So vector int g Hopefully we all remember this from our graph tutorial from 2 weeks ago. This is how we store a graph. And for a minus 1, we'll push back b minus 1, and for b minus 1, we'll push back a minus 1. Notice that I'm subtracting 1 from these nodes. These nodes are numbered from 1 to n. I'm actually going to label them from 0 to n minus 1. There's no real reason for this. This is sort of like a personal choice for me because I like to keep things 0 indexed, so I don't have to really think about whether something is 0 indexed or 1 indexed, which can lead to bugs. So we just 0 index our nodes. Then the next thing we need to do is need to construct our pre-ordering. Let's define our DFS here. We'll store where we're at and where we came from. And now we need to update sort of 3 variables here. We need to update parent of max n, because we need to find the, for every node we need to store its parent. And we also need to store the LNR for each node. What this LNR will correspond to, it will correspond to the range in our pre-ordering the subtree covers. For example, the L of 2 would be here. And if I actually were to label this array, 0, 1, 2, 3, this array is 0 indexed, but the nodes stored at each of it is 1, 2, 3, 4, 5. So if I looked at the L left of 2, I would get 1. And if I looked at the right of 2, I would get 5. You might be wondering why it's 2 and 5 and not 2 and 4, right? Because remember the subtree of 2 covers this range here. And the reason why that is because I'm using exclusive notation. Right, so what does that mean? So firstly, let's write this out. L of 2 is equal to 1. Right of 2 is equal to 5. This is inclusive exclusive notation. Basically what it means is that our range, this describes a range, right? Our range will include the left side, but it will exclude the right side. So when we look at this range, it starts at left, but it ends at 1 minus of the right side. So we're doing this. So you might be asking why we do this. Basically, all it comes down to is it makes the code look just a little bit nicer. It makes the maths just a little bit nicer, and so we like to do that. Another nice property that it has of using inclusive exclusive ranges. So if you ever want to find the size of a range, all you need to do, right, this is wrong. It should be 4. Sorry, my bad. Because we're looking at the index of the array 4. So 1 to 4, except it excludes the 4. So that's why it's 1 to 3. So as I was saying, one nice property about using inclusive exclusive is that if you ever want to find the size of a range, all you need to do is 4 minus 1, and you'll get 3, which is the size of this range here. If you use inclusive, which is what we're used to, which is saying the range from 1 to 3, then you have to subtract the endpoint from the start point, rather the other way around. You subtract the start point from the endpoint, and you have to add 1 to it as well, which is, a little bit ugly. Yeah, using inclusive exclusive makes the code just a little bit neater, and we're going to use that for both this range here and also for our range tree, as we're going to figure out soon enough. Okay, let's finish this DFS. First thing we're going to do is we're going to set the parent of at to equal from, right? The idea is that we're going to start our DFS at the root, and we're only going to go down. So the from will always be the node that we just came from, or in other words, the parent. Then we can loop through g of at, which is all the neighbors of at. If 2 equals from, we can use the same trick again that we did 2 weeks ago to make sure that we don't go back up the tree. And then we can DFS to the node. If we're considering the going back up the tree, then we can ignore it. Otherwise, if we're not going up the tree or going down, then we can DFS there. This DFS is by itself going to set the parent for every single node from the root. So that's nice and simple. I have to update left and right. So one thing to notice is that, let's say we look at the range of the subtree corresponding to 2, right? Notice that 2 is always on the left side of the range. So in other words, left of 2, or left of I really, is just the position in the pre-order that that node is in. Let's do it like this. So we'll declare a global variable for t. L of at is just going to equal to t. And then we'll increase t by 1. What this is going to do is that basically the first time we see a node, we're just going to set it to the very next available slot, right? So the left of at is going to be equal to the next available slot in t, right? So this is just going to give us the pre-ordering. So every time we increase t by 1. Afterwards, what we're going to do is we're going to run this for loop, right? And this is going to recurse down into DFSs. It's probably going to increase t, increment t a bunch of times within here as well. Once we come out of here, this t will be the same as the t that's over here, right? Because t is a global variable. And in fact, one thing we can notice is that, let's say we're at node 1, and then we recurse down here, this subtree, and then we recurse down here as well, right? And t will increment exactly the number of times for every single node that's under here. In other words, if t was like 1 over here, and after we, well, it should be 0. If t was 0 over here, after we increment through all of these, right, each of these nodes will lead to t incrementing by 1, including this one as well. So after we process this, t increments by 1, and then each of these will increment by 1 as well. So after we come back from this node, we'll get t equals 5. Right? And that just so happens to be the exact range of 1, right? At the beginning, t is 0. At the end, t is 5. This imaginary 5 at the end, but this is inclusive, exclusive. This just covers this entire range here. So we can just set r of at equal to t. So I know this might be a little bit confusing. It's really hard to think about recursion and pre-ordering and to be like sure that this is actually right. But one thing we can do is we can just confirm for ourselves by printing it out just to make sure that I'm actually not making this up and this is actually all true. So let's call our DFS first off. We'll call out the root and the previous will be -1. And for every single node, we're going to print out its parent plus 1, because remember we 0 indexed everything. So if we want to read it nicely, we have to plus 1 to everything again to make it 1 indexed. And we'll just do the same thing again for left and right. Except left and right don't actually get increased by 1. So if I paste in the tree from the sample input, we should get a bunch of parents and left and right. Okay, so looking here, it looks like I forgot to use using namespace std. So better make sure I do that. Okay, and we get the following. Printout. The first row corresponds to parents, and if we see, parent of 1 is 0 because it has no parent. Parent of 2 is 1, which is correct. We look back over here. Parent of 2 is, that's not the one, that's the range tree. This is what we want, this one here. Parent of 2 is 1. Parent of 3 and 4 are 2, which is correct. And the parent of 5 is 1. So this matches up. So left and right ranges, well, if you look at 1 here, the left and right for 1 is 0 and 5, right? That's this range here, so this is correct. For 2, it's 1 and 4, so that's this range here, so that's correct. For 3, it's 2 to 3, it's this range here, that's correct. For 4, it's 3 to 4, which is correct. And for 5, it is 4 to 5, which is correct. You can see how this parent variable is set correctly and the left and right variables are set correctly as well. That's how we do a DFS pre-ordering of our input. Okay, now that we have that, it's going to be really useful for us because now if we want to query the subtree of a particular node, let's say node I, we just query the range from Li to Ri. Right? We can just look at this array to know where the range starts and ends. Oops. Excellent stuff. Okay, let's handle the queries now. Running a little low on time, so let's speed this up a little bit. So we're going to scan in T and V, T being the type of operation and V being the node. We're going to subtract 1 from V since we zero indexed all the nodes, so we're going to make sure that we're working with the correct values here. And then we have to handle all of the cases. Okay, so now it comes to the hard part. We have to code up our tree. Okay, so let's do that. So we're going to declare a. So remember how before we had 3 values, root, dirty, and dirty add? I'm actually declared a node structure to hold all 3 of these together. So this should be a familiar concept from C. I think the syntax for the declaration is a little bit different. I can't remember what it was, but you had to do like type struct or something. I can't remember from C. You don't have to do that here. It's just struct node. C++. The naming convention is that we capitalize the first letter of a structure. We'll store int v, which is going to be the minimum of the range. That'll be these values over here. We're going to store bool dirty, whether it's dirty or not, and we'll also store a dirty set. This dirty set is going to remember what we should be setting everything below it to. So one thing we can notice about this struct is that every time we set dirty set, we're also going to set v to be equal to dirty set, right? The dirty set basically sets everything below to the value. These two things are just going to stay the same all the time. But in reality, we don't actually need dirty set. We can just use the value of v for a node to work out what we should set the children to. The dirty set is a bit obsolete, so we'll just store these 2 variables here in a node. Then we'll define a data structure root, which is range tree. It's of nodes, and we have maxn times 4. We only, in general, you need maximum number of nodes you're going to store in the range tree times 4, just to make sure that you have enough space in there. Okay, let's start with our cleaning function. So this cleaning function is going to take in I, it's going to take in L, and it's going to take in R. This will correspond to which node that we're at in our range tree, as well as the left and right range of what this range tree what this node covers. So for example, this node here, left to right range is 2 and 5. Remember, inclusive, exclusive. That's what the L and R are. Now we're going to try and push down. If this node is dirty, we're going to push down the dirt into its children. So first things first, if it's not dirty, then we can just return, right? We don't need to do anything. Okay. If L is smaller than R minus 1, that means that this node has children. If this node is a leaf, then L is equal to R minus 1. Remember the inclusive exclusive. But if this node has children, then L is smaller than R minus 1. So in this case, we want to push down to its children. So we just set the child of this child to be true, it to be true. That's how we use I times 2 here. That's one of the consequences of doing the level order, as you should probably know from just the normal range tree. We do the level order like this, label each of this node 1, 2, 3, 4, 5, 6, and 7. Then we can notice that the child of any single node is just equal to itself times 2, and then itself times 2 plus 1. You can confirm this again for node 3, for example. Find the left and right child of node 3. You can multiply it by 2 for the left child, which is 6. And multiply it by 2 plus 1 for the right child, which is 7. That's a nice property that we're going to be using to update the 2 children of our range tree. So range tree I times 2 dot dirty equals 2. Range tree I times 2 dot value equals I dot v. And we can just do the same thing again, but for the right child. Right, so we get to dirty, and we also make sure that we set its value to the correct value. So one thing to note about range trees, a very common pitfall, so you always have to be careful about which nodes hold the correct values and which ones don't. Right? You never want to do an operation using incorrect values. You only want to ever use a value after you're sure that it's correct. One thing I'm going to do here is I'm going to put an invariant here. If a node is dirty, the value is correct. Right? If a node is dirty, then the value is correct. What does this mean? Basically, it means that when I'm coming to this clean node, it's not dirty, then it's clean, so it's obviously correct. When I propagate it down, I'm going to set it to dirty, but I'm also going to make sure that its value is equal to the correct value here, right? It's equal to rti.v. So when I'm cleaning, I make the bottom two nodes dirty, but I also make sure the bottom two nodes have the correct value. So this is going to keep our invariant true here. We'll find that as we go on, this invariant is going to be very useful for us. I want to be a bit more specific. Technically, what it should be is if a node is dirty and it has no dirty ancestors, the value is correct. Because of course, if this node was dirty, but there were dirty nodes on top of it, then the value isn't correct. Okay, so that should be our clean function. And we just make sure at the end, we set the dirty to false. Okay, so our file says, okay, do we set it to V or just 1? If we set a range to 1 and then immediately set the same node to empty. Okay, interesting question. So now what happens if we try to set a range to 1 and then set the range to 0 again? The thing is that before we ever come to a node, we're always going to clean it, right? Okay, let's do it for an example. This might be the easiest way to do it. It's going to be our range tree. We're going to set everything 0 at the moment. This is a min tree. So of course, every node is the min of its 2 children. So let's say we want to set this range to 1. Right? So we'll come down, we'll find the relevant nodes, we'll mark these as dirty, and we'll set these to 1 like this. Okay. Now, let's say we want to set this entire range all to zeros, right? So we'll come to this node is the relevant one. We'll come to this, make it dirty, and we'll set it to 0. Actually, before we do that, I have to make sure we update. Well, these values are actually correct, so they're fine. So yeah. Then we set this to 0, right? And so now you're wondering what happens if, like for example, this node we set it to 1, but we immediately set it back to 0, right? And what happens? Well, we can really easily find out. So let's say we want to query this node, right? So what's going to happen is that we're going to start over here. The first thing we're going to do is we're going to clean it. So when we clean it, we're going to set both of its children to dirty. We're going to set its value to 0. And then, well, these things don't, and we're going to set sort of dirty set to 0. Oops, that's 1. And this dirty set is the same thing as the V because we're not actually storing that. So we're just going to do that. We're just going to override it with a 0 instead. And so because this is a set operation, right? We're setting everything here to 0. And that means that we are okay with overwriting everything that's inside here, right? Because even if like before this was dirty and we want to set everything below here to 1, it gets sort of overwritten by the fact that we want to set everything to 0 instead. But this just becomes a 0, and that's why we overwrite it. Does that answer your question? Does that make sense? Somewhat. Okay. So another thing, you did mention that why not just set the range to 1 like this, right? Why not set it to 1? Well, I want the value to be the value that we're setting it to. So V can either be 0 or 1, right? Because sometimes in this command, we might want to set an entire range to, this range update. We might want to set an entire range to 1, right? Fill subtree with 1s. Sometimes we want to update a vertex to be 0. So that's why want to actually use rti.v here, not just one every single time. If it was just one every single time, then we would have no way of setting a 0 in our subtree. So we need to use rti.v to propagate the value of this node down to all of the other ones. Okay, so I'm just going to move on here. Next I wanted to quickly talk about is how we handle moving dirty values onto other dirty values. So remember how in our first example, when we did the dirty add, we had to store this dirty add variable and we had to add to it, right? In this case, we're just overwriting the variables instead. So basically, what I'm saying is that you have to be very careful about how you move dirt onto other dirty nodes. Right? Sometimes they'll have weird interactions, so you have to make sure that you program in those interactions perfectly. So if you move a dirty value onto another dirty value, what it looks like. In this particular case, when we move a dirty value onto another dirty value below it, we just overwrite it with our current v. So that's the desired effect. Okay, that should be our clean variable done. I mean, our clean function done. Let's look at a query. So we're gonna get this query into QL. This is going to the left and right side of the query, again inclusive, exclusive. I'm also going to take in L, and R. These will represent the same ones as this clean here. The node we're at and the left and right range of this node. Okay. The first thing we want to do at any node is always to clean it. And this will make sure that this node holds the correct values, and we push all the data down to its children. Just to make sure that we're always looking at the correct values. Okay. If L equals QL and R equals QR, then just return rti.v. Right? Since we cleaned it, we know that this node now holds the correct values. And so we can just return rti.v. Otherwise, we'll find the midpoint. This is all standard range tree stuff. We'll declare a variable called res for result. And we'll just set res to equal the minimum of looking to the left and looking to the right. If query left is less than m, in other words, let's say this node covers this range here. We have an L and an R. Just calculate the midpoint, and this might be our query range. So this is QL and this is QR. So if query left is to the right of m, then we have to look into the left left subtree of this node. If QR is larger than m, then we have to look into the right subtree of this node. Let's just do that. If QL is smaller than m, resident equals the minimum of result and query QL min m and QR I times 2, L and m. Remember I times 2, we can use that to look into the left child. And m will be the new ranges that we pass into this node as well. Let me do the same thing in reverse. It's actually easy to just type this out again. L is larger than m, result equals minimum result query. We take the maximum of m and QR this time. QL I times 2 plus 1 m r. So that recurs to the right side. I take the minimum of both of these, return the result. That should be our query function. One more thing that we can do to make our life a little bit easier is that every time that we want to call query, initially at least, we generally want to start, not generally, but we always want to start at the top node. That corresponds to I equals 1, L equals 0, and R equals n, right? This is the range from 0 to n, and the root is always at I equals 1. So if we do this here, if we write this equals 1, equals 0, equals n, these are what's called default arguments, which means that if we call query with only 2 arguments, it's just going to fill in the rest of these with these default arguments here. Notice that inside query though, actually to call the rest of these. So this is just going to override the default arguments if we actually specify arguments for them. But if we don't, then it's just going to use these as the default. This is going to be useful for us because then we can call query with just 2 of the numbers instead of having to specify 1, 0, and n from the top. So that's the query function. Let's finally move on to the update function. The update function is going to take a left and right range. It's also going to take in a value to set to. We're going to clean this range. We're going to look if the current range matches the update range. What we're going to do is going to set the dirty to true. Then we're going to update the v to be the correct value, right? We're going to update v to be equal to the v that we want to set this entire subtree to. Remember, this is going to keep our invariant true. If I notice dirty, it has no dirty ancestors, the value is correct. So when we're at node I, we know that it has no dirty ancestors because we've been cleaning all the way down. We also know that this is dirty, and we've also set the value to be correct. So that means that our invariant is true, right? But our invariant is still true here, and clean also preserves our invariant. So that means that our invariant is going to stay true for the whole runtime of our program. Okay. Next, we just do standard update stuff. This is going to be looking very similar to the update side of things. Oops. UL and M here. And we have items. Look at the left, L and M. If UR is larger than M, update the right side. So the maximum of UR and M, or UL and M rather, that should be UR. Let's make sure I did it correctly over here as well. No, I totally bungled it. Should be QL and QR there. Yeah, there's the correct values. And we'll look to the right side. So now just update both sides. And after we've updated both sides, we have to make sure that when we're going back up the tree, our tree holds the correct values now. So rti.v equals min rti times 2 v rti times 2 plus 1 dot v, like that. Just take the min of its 2 children. This will make sure that it's updated. Hi, Jonathan. We're just about finished with coding this part, and we'll move on to the problem set stuff. Okay, I think that's actually the final line of code. No, it's not. We have to make sure we handle the queries properly. That's pretty easy for us. Bool empty node equals. So we're going to check if this range has a 0 in it or not, right? Because remember, when we do a fill, check a range to see if there are any zeros in it. If there are any zeros, we push it to the parent of v, and then we fill the subtrees with 1s. So if this is empty, we query, check to see if it's 0 or not. Notice here that we're using left of v and right of v, right? Be very careful when doing this. We have to make sure that we use left of v and right of v. A very common mistake is to use like v here instead of left of v. Right? Remember, we have to use left and right to convert it into a range on this pre-ordering here. Okay, so empty node is going to store if the range has an empty node or not. If empty node and v doesn't equal to 0, in other words, it's not the parent, then we'll update the parent by setting it to 0. So update the parent of v. And we'll set it to 0. Once again, make sure we use L here. Don't just set parent v and parent v plus 1, right? And finally, once we've moved it to the parent, and L of v, R of v, 1. We set this range to 1. For the next part, we update, set a point to 0. So this is very easy. L of v plus 1 is how we find a range length 1. We just set it to 0. That's the v value that we're going to pass in. And finally, for the query, we just need to print out if there is a 0 there or not. So just query this range. So if the min is 0, that means there's a 0 there. So that means this node is empty. If the minimum is 1, there's no zeros, this node is full. So that should conclude the code. So let's try and run it. Looks like I'm getting some errors here. Too few arguments to update. Right, so I've forgotten to pass in the v as well. We've got to make sure that we pass in v to all of its children while we're going down the tree. So pass in the same v again. Here, too few arguments once again. Because I haven't set default values. So it's expecting 6 arguments, but I've only passed in 3 here. The way we solve this is by setting default values. So this basically means that when we call it down here with no the last 3 values missing, it's going to set these as the default. Okay, so we got an output. I have to check whether it's the same or not. 0, 0, 0, 1, 0, 1, 0, 1. 0, 0, 0, 1, 0, 1, 0, 1. So it looks like our output matches. I think I'm submitting the wrong code. No, I'm not. I'm submitting nothing. Let me choose the file. Wait a bit. Running on the tests. And it got accepted. Very, very nice. Okay, so are there any final questions about this code? I'll make sure to get the paste bin sorted during the breakout groups. If you think you have a question to ask, if any, I'll ask you which problem that you're up to right now. I'm assuming most people are on A, looking at VJudge. Most people haven't actually started yet. Can everyone please vote on which problem that they're up to, which they're doing. Felix, Jonathan, I need you to vote as well. The bounce, fair enough. All right, goodbye, Felix. See you next week. Okay, we have a even mix of 1 and 2. Great, excellent. So I'll just make the breakout rooms then. And you can proceed to work on the problems.